Imagine a world where a simple scratch could kill you and where childbirth was a deadly gamble for mothers. A soldier's wound, moreover, frequently meant almost certain death. This perilous reality plagued humanity for thousands of years, until one September morning in 1928. Then a messy laboratory would fortuitously change everything forever. The story begins in London at St. Mary's Hospital, where Alexander Fleming, a Scottish bacteriologist, was known for his brilliant mind. He was equally known for his incredibly untidy lab. While his colleagues kept pristine workspaces, Fleming's benches were cluttered with unwashed petri dishes and forgotten experiments. Fleming had spent years studying Staphylococcus bacteria, the microscopic killers responsible for infections that tragically claimed millions of lives. He earnestly searched for something. He desperately sought anything that could stop these deadly microbes, but progress was slow, and answers seemed impossibly far away. The medical world desperately needed a breakthrough now. In early September 1928, Fleming took a holiday with his family, leaving his laboratory exactly as it was. Dishes were stacked and cultures still growing. He also left windows slightly open to the London air, not realizing that this seemingly ordinary carelessness would soon lead to one of history's most important discoveries. When Fleming returned on September 3rd, he began the tedious work of cleaning up his abandoned experiments. He meticulously picked up petri dish after petri dish. He was examining the bacterial cultures before tossing them into disinfectant. This was routine work, the kind scientists do without thinking, until one specific dish made him abruptly stop. Something strange had happened in this particular dish. A blob of mold had contaminated the Staphylococcus culture, probably floating in through that open window. But here's what caught Fleming's trained eye. Around the mold, there was a clear ring where absolutely no bacteria grew. The deadly microbes had simply vanished. Most scientists would have cursed the contamination and thrown it away. Fleming's messy habits had certainly ruined experiments before, but his trained eye recognized something extraordinary. This mold wasn't just growing alongside the bacteria, it was actively killing them. Something potent in that fuzzy green blob was clearly a bacteria destroyer. Fleming immediately began investigating, identifying the mold as belonging to the Penicillium genus. This was the same family that often grows on old bread and rotting fruit. He carefully cultured it, growing more of the mold and testing its effects. The results were astonishing, as this substance killed multiple types of deadly bacteria. He called his discovery penicillin, and in 1929, he published his findings in the British Journal of Experimental Pathology, describing this mold juice. This juice could destroy bacteria while being relatively harmless to human tissue. It seemed like the miracle cure humanity had been waiting for, but then, tragically, nothing happened. The medical community barely noticed Fleming's paper. Colleagues congratulated him politely, then moved on to other research. This was because Fleming faced enormous, unseen obstacles. Penicillin was incredibly difficult to produce in useful quantities, and it degraded quickly, an immense challenge. He simply couldn't extract enough pure substance to conduct proper human trials. Fleming tried for several years to refine penicillin, but he was fundamentally a bacteriologist, not a chemist. The immense technical challenges consequently overwhelmed him. The mold produced only tiny amounts of the active substance, and isolating it required sophisticated chemistry far beyond his expertise. His miracle cure remained trapped in petri dishes. Meanwhile, the stakes couldn't have been higher. Every day, people died from infections that we now consider trivial, such as a child's scraped knee. Pneumonia was a death sentence. Surgeons performed operations knowing that even if they succeeded, infection would likely kill their patients anyway. Medicine desperately needed an urgent answer. By the mid-1930s, Fleming had largely abandoned penicillin research, returning to other projects. He occasionally mentioned his discovery in lectures, making no real progress. The miracle mold gathered dust in his laboratory, its immense potential unrealized. It seemed that Fleming's accidental discovery would tragically become just a footnote in medical history. But then in 1938 at Oxford University, a new challenge emerged when Howard Florey and Ernst Boris Chain began researching antibacterial substances. They systematically reviewed old scientific papers, looking for forgotten discoveries that might hold promise. Then, they finally found Fleming's penicillin article among the archives. Chain and Florey saw what Fleming couldn't achieve alone: the sophisticated chemistry needed to purify and produce penicillin in usable quantities requiring expertise. They assembled a team of brilliant scientists and began the painstaking work of turning laboratory curiosity into practical medicine. However, the timing tragically couldn't have been worse. In September 1939, Nazi Germany invaded Poland, and Britain plunged into World War II. Suddenly, Florey and Chain's important work took on desperate urgency. War meant massive casualties. Millions of wounded soldiers would face infected wounds. If penicillin could be mass-produced, it could potentially save countless lives on the battlefield. Wartime Britain offered terrible conditions for research, with resources scarce, funding tight, and German bombs raining down on British cities daily. The Oxford team worked in cramped laboratories with makeshift equipment, growing penicillium mold in bedpans, milk bottles, and ceramic vessels, anything that would hold culture medium. By early 1941, they had produced enough penicillin to attempt their first human trial. The patient was Albert Alexander, a 43-year-old policeman dying. He suffered from a massive infection that started with a simple scratch from a rose thorn, spreading throughout his body, destroying tissue, and causing abscesses. He had mere days to live. On February 12, 1941, doctors carefully injected Alexander with purified penicillin, beginning the critical trial. The initial results were nothing short of miraculous. Within 24 hours, his fever dropped, his appetite returned, and the infection began clearing remarkably. After 5 days of treatment, he was recovering exceptionally well. But then disaster struck. The Oxford team had used their entire supply of penicillin on Alexander, even recycling it from his urine to extract every precious molecule. They had no more to give him. Without continued treatment, the infection roared back with terrible fury. Alexander's condition tragically deteriorated rapidly, and he died. The team was devastated, yet they had proven something crucial. Penicillin could indeed cure deadly infections in humans. The problem was not the medicine. It was production. They urgently needed industrial-scale manufacturing, massive resources, and advanced chemistry to create enough penicillin to truly save lives. And they needed it fast. In 1941, Britain simply didn't have those resources. The country was under constant bombardment, and factories were repurposed for weapons, stretching chemical plants to their limits. Florey and Chain realized with sinking hearts that their own nation simply couldn't manufacture penicillin at the immense scale needed to truly make a difference. So they made a desperate decision. They would travel to America, a dangerous journey across U-boat-infested waters. They simply had no other choice. America had the vast industrial capacity, the money, and the essential resources that Britain desperately lacked. If penicillin was going to save countless lives, it would ultimately have to happen there. When Florey arrived in the United States in July 1941, he carried with him precious samples of the mold and detailed re-notes. He was alone. He met with American officials, pharmaceutical companies, and re-institutions pleading his urgent case. This medicine could change everything, he told them. But would they truly listen? At first, the response was lukewarm. American pharmaceutical companies were highly skeptical about investing millions in a mold extract that might not even work at scale. The fermentation process was incredibly difficult, yields were unpredictable, and nobody knew if mass production was even possible. Florey faced bitter rejection after rejection. Then came December 7, 1941, Pearl Harbor. Everything changed overnight as America was suddenly at war, causing a national awakening. Suddenly, the military understood exactly what Florey had been saying. Soldiers were dying from infected wounds, not just from bullets. Penicillin became a strategic military necessity. The U.S. government threw its full weight behind penicillin production, creating the War Production Board Committee. They brought together pharmaceutical giants like Pfizer and Merck. It swiftly became a national priority, with funding and resources that dwarfed anything Britain could have mustered. The urgent race for penicillin production was unequivocally on. Even with unlimited funding, the scientific challenges were truly staggering. The original Oxford method used flat, ceramic vessels, essentially laboratory dishes, to grow the mold. To produce enough penicillin for even one hospital, you'd need thousands of these vessels, taking up entire warehouses. It was completely impractical for any mass production. American chemists and engineers tackled the problem from every imaginable angle. They experimented with different strains of the mold, searching for varieties that produced more penicillin. They tested thousands of growth media recipes, trying to find the perfect nutrients to maximize yield. Progress was often slow and frustrating, measured in tiny incremental improvements. Meanwhile, a researcher at the Northern Regional Laboratory in Peoria, Illinois, made a breakthrough discovery, adding corn steep liquor to the growth medium. This cheap byproduct from corn processing dramatically increased penicillin production. Suddenly, the yields jumped tenfold, making large-scale production seem actually possible. This was a true game changer, but they still urgently needed a better strain of mold. Researchers thus began what they called the global mold hunt, collecting soil samples from around the world. They tested thousands of different penicillium varieties, hoping to find one that naturally produced more of the miracle substance. It was painstaking work with no guarantee of eventual success. And then, in one of history's greatest ironies, a lab assistant in Peoria found the winner. Not in some exotic location, but on a moldy cantaloupe. This moldy cantaloupe from a local grocery store yielded Penicillium chrysogenum, which produced 200 times more penicillin than Fleming's original. It was just sitting there on rotting fruit. With the right strain identified, engineers at Pfizer developed a revolutionary new production method using deep tank fermentation. Instead of flat dishes, they used massive steel tanks. These massive steel tanks, thousands of gallons each, featured controlled temperature, pH, and oxygen levels. It was essentially industrial-scale brewing, adapted for growing mold instead of making beer. Even as production ramped up, there was still a critical problem. The penicillin molecule itself was incredibly fragile and unstable, degrading quickly and losing potency. It was also destroyed by stomach acid, meaning it couldn't be taken as a pill. Patients thus urgently needed injections, and the medicine frustratingly had to be used fresh. Chemical teams worked desperately to understand penicillin's molecular structure. If they could figure out exactly how the molecule was built, they might stabilize it. Penicillin's structure was maddeningly complex, unlike anything they'd encountered before, and it stubbornly resisted every attempt at analysis, a formidable scientific challenge. Time was running out. By 1943, the Allied invasion of Europe was being planned, and military doctors knew that casualties would be tragically massive. Without penicillin, thousands of soldiers would die from infected wounds that should have been treatable. The pressure on pharmaceutical companies became almost unbearable. They had to deliver soon. Production facilities worked around the clock. Pfizer converted an entire ice-making factory in Brooklyn into the world's largest penicillin plant, a monumental transformation. Workers operated in shifts, monitoring massive fermentation tanks 24 hours a day. Every precious drop of penicillin was carefully extracted, purified, and rushed to military hospitals. By early 1944, American factories were producing about 100 billion units of penicillin per month. It sounds like a lot, but it was barely enough. Every ampoule went to the military first. Civilian doctors had to patiently wait. Cancer patients, children with infections, accident victims, they all took a back seat to the war effort. Then came D-Day, June 6, 1944, as Allied forces stormed the beaches of Normandy. Combat medics carried penicillin with them directly into battle. For the first time in human history, soldiers wounded in combat had access to an antibiotic that could stop infection before it became deadly. This was a critical turning point. The results were stunning. In World War I, infected wounds had killed thousands. Men survived initial injury only to tragically die days later from gangrene or blood poisoning. But in World War II, with penicillin available, the death rate from bacterial infections plummeted significantly. Wounds that would have been fatal became survivable. Stories spread of miraculous recoveries. A soldier shot through the leg, infection raging, fever spiking, was given penicillin and walking again within days. A pilot with pneumonia, struggling to breathe, was saved by injections that his father's generation never had access to. Penicillin became widely known as the wonder drug. Even as it saved thousands on the battlefield, penicillin remained scarce for civilians back home. American pharmaceutical companies faced an impossible, agonizing choice. Should they continue prioritizing military use or start making it available to desperate patients at home? This agonizing ethical dilemma persisted, for either choice meant someone would die. The U.S. government maintained strict rationing, requiring doctors to apply for permission to use penicillin. They had to prove their patient's case was dire enough to justify allocation. Parents watched their children suffer from treatable infections while knowing a cure existed, but was reserved for soldiers. The frustration among civilians was immense. Meanwhile, researchers were still struggling to crack penicillin's chemical structure. Dorothy Hodgkin, a brilliant British crystallographer, led the effort using X-ray diffraction. This technique involved bouncing X-rays off crystallized penicillin to reveal its molecular architecture. It was incredibly complex work, requiring years of arduous calculations done entirely by hand. In 1945, Hodgkin finally succeeded, revealing that penicillin contained a beta-lactam ring, a four-atom structure nobody had predicted, defying chemical wisdom. This ring was the key to penicillin's antibacterial power, the molecular weapon that effectively destroyed bacterial cell walls. Understanding its elegant structure changed everything. With the structure now known, chemists could finally begin developing synthetic methods and creating more stable derivatives. They started modifying the molecule extensively. They created new forms of penicillin that lasted longer, resisted stomach acid, or targeted different types of bacteria. The age of antibiotics had truly begun, opening incredible possibilities. By the war's end in 1945, American factories were producing enough penicillin to treat both military and civilian populations globally. The price also dropped dramatically. What had once been rarer than gold became available in every hospital and pharmacy. Fleming's accidental discovery was miraculously transformed into a global, life-saving medicine. The impact on medicine was truly revolutionary. Diseases that had killed for centuries, bacterial pneumonia, syphilis, scarlet fever, became treatable and often fully curable. Surgeons could perform operations that would have been suicide before antibiotics because post-operative infections were no longer a death sentence. Life expectancy jumped dramatically. In 1945, Fleming, Florey, and Chain were jointly awarded the prestigious Nobel Prize in Physiology or Medicine for their groundbreaking contributions. It was a rare instance where the prize was shared among multiple researchers. Acknowledging penicillin's journey from curiosity to medicine required many brilliant minds. Fleming, typically modest, used his Nobel acceptance speech to issue a profound warning. He cautioned that bacteria could become resistant to penicillin if used carelessly. He warned that resistance could occur if doses were too small or treatment stopped too early. It was a prescient warning, one that would prove tragically accurate. But in that triumphant moment, in 1945, the world celebrated penicillin. It represented hope, proof that science could triumph over ancient killers. Human ingenuity could unlock nature's secrets and them into healing, transforming lives. The darkest hours of war had given way to breakthrough, with millions saved. In the years following that Nobel Prize, penicillin's impact accelerated beyond anyone's predictions. By the late 1940s, companies produced billions of units annually. The antibiotic that had once been impossibly rare now sat on pharmacy shelves everywhere. Infections that had routinely killed, pneumonia, sepsis, became treatable almost routine. Hospitals transformed virtually overnight. wards filled with dying patients now saw recoveries that seemed miraculous, a testament to penicillin's power. Childbirth became safer as puerperal fever, the bacterial infection that had killed countless mothers, yielded to penicillin's power. Life expectancy began climbing. Fleming himself became an international celebrity, traveling the world to receive honors and give lectures, a testament to his groundbreaking work. Yet he remained modest. He always emphasized that penicillin's success belonged to the entire team and warned audiences repeatedly about one grave danger: the emerging threat of resistance. Even in his Nobel lecture, Fleming sounded the alarm. Describing how bacteria could adapt, he warned that misuse could train microbes to survive. It was a prophetic warning that few took seriously in those euphoric years. The miracle drug seemed invincible, and humanity felt it had conquered the microbial world. Penicillin's legacy extended beyond treating infections. It fundamentally changed how scientists approached drug discovery, proving that nature held compounds of extraordinary therapeutic value. Researchers began systematically screening samples, hunting for the next wonder drug. This effort yielded streptomycin for tuberculosis, tetracycline, erythromycin, an entire arsenal of antibiotics. Fleming lived to see this golden age unfold, witnessing his accidental discovery spawn an entire field of pharmaceutical research. He saw tens of millions of lives saved. When he died in 1955, at age 73, he was mourned globally as one of humanity's great benefactors. His ashes were interred in St. Paul's Cathedral. Today, more than 90 years after Fleming's odd discovery, penicillin and its descendants remain cornerstones of global health. Millions of prescriptions are written annually. Countless surgical procedures, cancer treatments, and emergency interventions depend on antibiotics to prevent or fight infections effectively. The world Fleming's curiosity helped create is almost unrecognizable. Yet his warning about resistance has proven tragically prescient. Antibiotic-resistant bacteria now kill hundreds of thousands annually, a growing global health crisis. Scientists race to develop new drugs as old ones lose effectiveness. This battle between human ingenuity and microbial adaptation continues, demanding curiosity and determination. The story of penicillin endures because it captures something essential about scientific discovery. Breakthroughs often come from unexpected places. Luck favors the prepared mind. Solving one problem reveals new challenges ahead. Fleming's contaminated plate changed the world, not by ending the fight, but by giving humanity essential tools and hope.